Hello, everyone. My name is Marco Pavone, and I'm a faculty at Stanford University, where I direct the Autonomous System Lab. It is my pleasure to introduce Byron Boots as one of the recipients of this year's RSS Early Career Award. This award recognizes the contributions of early career researchers to the field of robotics. I was indeed a recipient of the RSS Early Career Award in 2019, so I'm familiar with the sense of honor and pride that this award entails. Byron exemplifies the meaning of the RSS Early Career Award in several ways. He's currently an associate professor at the University of Washington, where he directs the Robot Learning Laboratory. With his research, he has made fundamental contributions to the field of robot learning by bringing together an impressive set of techniques, from machine learning to control theory, even to quantum physics. He has received several awards, including Best Paper Awards from the RSS conference, and he's very actively involved in the community. For example, he is co-chair of the IEEE Robotics and Automation Society Technical Committee on Robot Learning. And if all of this is not enough, he also bridges the gap between academia and industry by serving as a principal research scientist in the Seattle Robotics Lab at NVIDIA Research. Without further ado, I leave the stage to Byron, and I'm excited to learn about his latest results. Should you have questions, please use the Q&A functionality embedded in Zoom. Thank you, Byron, and congrats for the award.
Wow, thank you, Marco. Thank you for that introduction. It's a great honor for me to be here, and I'm really humbled to be giving this talk. So today, I want to talk about two subjects that are near to my heart. That's machine learning and robotics. And the purpose of this talk is to provide some personal perspectives on problems at the intersection of these two fields. I'll also present a couple of ideas and hopefully some food for thought. So for a long time, I've been interested in artificial intelligence and machine learning. And for the last 8 years or so, I've specifically been interested in designing intelligent robotic systems. And I believe there's at least 3 different ways that you can go about doing this. So on the left here, what I've labeled as models is basically what I think of as like automation and classical robotics. So it includes things like using accurate models and simulation, knowledge of mechanics and controls, and it relies heavily on prior knowledge of the system as well as task environment engineering. So these methods are very efficient in terms of compute, but brittle in the face of changing properties of the system or the robot or its environment. So on the right, we have a totally different strategy, which is just using machine learning. So more specifically in the context of this talk, I mean model-free reinforcement learning. And the idea here is that we can learn how to behave directly through a robot's interaction with its environment. And this can work really well for generating behavior where it's not easy to write down a model a priori, but unfortunately can also be really expensive in terms of data and compute compared with model-based approaches or automation. Then finally, at the top of the triangle is an important area of robotics that I think is often overlooked by people who are really focused on AI, and this is teleoperated robots. So there are many successful robotic systems that have extremely capable hardware but rely on human expertise for decision-making. So in summary, these are 3 very different ways of approaching robotic intelligence. We can use models, planning, and control. We can use machine learning, or we can just develop capable teleoperated systems and let a human make the decisions. And these are often viewed as being at odds with each other. But to me, all of the interesting questions are really where these areas might intersect somewhere near the center of this triangle. So we're already familiar with some of these intersections, such as adaptive control, imitation learning, and human-in-the-loop models. So today, I really want to focus on 3 different approaches to designing robot behavior and how they can be related through online learning. I'll talk about model predictive control. I'll talk briefly about reinforcement learning, and then I'll discuss imitation learning. And I'll do it from this online learning perspective. Along the way, I'll also want to discuss how simulation and prior knowledge can be combined with data for designing more effective robotic systems. And I want to stress that this online learning view is a perspective. It's one of many possible perspectives, but I think it's a particularly interesting one. So before I get started, I also want to provide some context for how I tend to think about robot learning problems. So first, I'm a big fan of the no free lunch theorems, and my belief is that machine learning basically works because of structure. And this is all true, right? So this is very general and I think a fairly uncontroversial statement. Algorithms that work well have structure in the function or policy class, in the objective function, in the training or testing data sets, or in the learning algorithm itself. And often algorithms which are very effective in machine learning have a lot of structure. So I think this is actually good news for robot learning. Robots and the tasks that we're considering as roboticists have a lot of structure in them. And the question is, how do we make choices for our machine learning algorithms that can exploit this structure? So let's think about robot learning in the abstract, and then show different places where we have structure in the robot and how it collects data, and then think about ways of doing machine learning for robotics. So we're going to start with just a robot. And usually we can assume that the robot can perceive the environment and take actions that change its relation to the environment. So this is the basic robotic paradigm. It's basically what I learned as an undergrad. But for robots that adapt their behavior with experience, we need to break this down a little bit further. So we can usually call the function that takes states or observations as input and produces actions as output a policy. And the policy itself has parameters which are indicated by theta here. And if the parameters stay the same, then the robot's behavior stays the same, right? So if you put the robot in the same location in the environment, it's going to produce the same behavior. But if we want robots that can learn from their mistakes and handle complex dynamic environments, then we can additionally specify a learner that updates the policy parameters to improve at some task with experience. So the learner can receive feedback from the environment, so that's going to be like the state on the left. And it also has access to an objective function for the task that we're trying to solve. So the objective basically just tells us how good the policy is and guides the learner. Okay, so this is one way of thinking about an adaptive robotic system where we've really highlighted the robot's relationship to the environment. I'm sort of a machine learning guy at heart, so I alternatively want to kind of reframe this a slightly different way, where we're focusing on the learner and how it interacts with a complex system which consists of the policy and the robot in its environment. So there's a little bit of a change, but the idea is that the learner is going to be making decisions about policy parameters based on feedback that it gets in the objective function. So to make things a little bit cleaner, I can just compress the policy's interaction with the environment down into this little system box here. And now think about like, what are we trying to do with our learning algorithm? So one way to think about the learning problem is through the lens of online learning. And the idea here is that every round, every round of online learning could be, for example, something like a time step in our system or an episode before resetting. So for every round, the learner chooses a parameter theta and executes a policy with those parameters in the system. And now we can observe what happens by looking at this output from the system, or this state, this feedback that we get from it. So we can think of the system basically as an adversary that provides feedback to the learner by picking out a loss function. So I'll discuss how this works in a few slides a little bit later. Finally, the learner will update the parameters based on the loss, and then this process repeats. So there's this kind of like nice interactive feel to this problem where the learner is constantly trying to update its parameters in order to perform better in the system. So why does this online learning type framework make sense for robotics? So we can step back and think carefully about how robots should learn and how robot learning problems are a little bit different from learning problems that you often encounter in machine learning. So empirical risk minimization is the dominant paradigm for thinking about machine learning algorithms. It's often used to guide how we think about basic machine learning problems like classification and regression. But in my view, it doesn't make a whole lot of sense for robotics problems. So first, robotics data is often not independent and identically distributed. So robots are collecting data that is evolving over time, and they're interacting in closed loop with the environment. So there's all of these correlations in the data which are difficult to deal with. Second, data is often not collected in batch in practice, but it's streaming and collected through the robot's interaction with its environment. And then finally, the models that we try to learn in robotics are necessarily approximate. So the data generating process typically does not live in the model class that we're trying to fit. So these are all things that we kind of have to deal with when we're thinking about learning problems in the robotics domain. Now, unlike empirical risk minimization, online learning is a framework which makes very minimal assumptions. So it's mainly focused on the concept of regret minimization. So for stationary policies, we want to learn a policy that works everywhere in the environment, and minimizing regret means learning a sequence of policies that compares well with the best policy in my policy class in hindsight. So in other words, I want to learn very rapidly. I want to do the best that I can given my policy class and the data that I've seen so far. So for non-stationary policies, I can think of something similar. So I want to learn a policy sequence now that is performing as well as possible with respect to the best sequence of policies that I could have executed. So the idea is I'm trying to track like the best policy over time in my system. And this is a much harder notion of regret to minimize. So online learning focuses on notions of regret like these, but it's also very general in that it does not make the IID assumption. And online learning is agnostic with respect to the ideal system. So I'm just trying to learn the best policy in my policy class. Okay, so returning to our diagram of the learner and its interaction with the system, at this point I want to make a few additional observations. So first, the state or feedback that we get from the system when we execute a policy is typically not actually state at all, but rather some sort of partial observation of state. So for example, an image does not contain full information about the state of a robot and its location in the environment. So this sort of thing can cause difficulties. There's a few other things which are a little bit difficult about our particular setup with robotics. So the second is that the objective function, this is something which can be hard to optimize, but there's something which is good about this, which is that our objective function is generally subjective. So when we're trying to get a robot to learn, we need to design an objective function and hope that it works. So if the objective function doesn't work well, we can just change it. And this is really important. So different objectives can have a significant effect on our learning algorithm. Examples include things like reward shaping in RL or imitating an expert rather than solving a full reinforcement learning problem. Finally, it can be hard to predict what will happen when I actually update my parameters. So if my system or policy is complex, changing the parameters may result in unexpected and costly behavior. So think about like a walking robot which may fall over or an autonomous vehicle crashing. And ways of mitigating this include using interpretable policies or engineering the task environment so that the robot's interactions are safe, simple, repeatable, and predictable. Now, if we can predict the outcome of changing policy parameters, then learning in simulation is another good option, right? So it's potentially a very powerful way to generate data for a machine learning algorithm that just costs us less, right? So it allows us to update parameters cheaply without having to run real-world experiments that can be very slow and costly. So once a policy is learned, like if we learn it in simulation, we can then run it in the system, possibly tweak it slightly. And this is the idea behind sim to real. So this is a very powerful and increasingly popular approach. But we can do more complicated, interesting things as well, right? So alternatively, we can use a simulator during training and update the policy based on information gained from both the simulator and the system. And a more advanced version of this uses the system to update the simulator itself so that it provides better data that the policy can learn from. Okay, so I just wanted to sort of give you that overview of how I've been thinking about some of these problems, like optimizing policies and where a simulator comes in and what the role of simulation is. And I'll come back to this, but At this point, I want to switch gears and discuss how some of these ideas can be used to solve interesting robotics problems. So here's one of the robots that we had at Georgia Tech. So it's a high-speed off-road ground vehicle built in collaboration with several labs in computing and aerospace engineering at Georgia Tech. And our goal is to autonomously race this vehicle faster than a human can pilot it on dirt tracks. So just to give a little bit more information about the platform, basically it's a 1/5 scale truck, so it's about 1 meter long. It weighs about 45 pounds. It has electric motors with a top speed of somewhere in the order of 50 miles an hour. It has cameras, IMU, GPS, wheel speed sensors, and considerable onboard computational resources. So it has a good CPU and a GPU, which can be used for computing a policy. So we can control the car by steering and modulating speed with throttle commands. And this is basically our platform that we want to drive really, really quickly on things like dirt tracks. Okay, so we have this great hardware. How do we now design a policy that will control this car at high speeds and do so without crashing, right? So how do we turn sensor data into motor commands? So before I talk about how we actually solve this task, I want to give you an illustration as to just why it's hard. So I'm about to show you a slow motion video of the dynamics of our car as it's taking a turn at high speed. And so one of the things that you may be able to see here is that it's bouncing and sliding. This is behavior which is really hard to predict and virtually impossible to simulate accurately from first principles, at least fast enough for it to be useful. So we can think of trying to find a policy to control the vehicle as actually online learning in this case, where the learner is tasked with choosing a good sequence of policy parameters. And these parameters are evaluated by the robot and its interaction with the world. So we're going to first try to solve the problem of controlling the vehicle with MPC, and then we're going to move on to a couple different other ways and think about how they're related. So how do we design a policy for a high-speed ground vehicle? Well, despite what some of my machine learning colleagues may tell you, classical engineering is generally a very good starting point for this kind of problem. So we're going to start by decomposing the problem into individual unit-tested components. And in our current setup, the pipeline looks something like this. So we're using perception, which is based on GPS and IMU, which gives us accurate outdoor position to within a few centimeters. Our state estimation consists of localizing the robot with respect to a GPS survey of the environment. And then we're going to assume a simple predictive system model. This is actually something that we can learn some of the parameters for from data, and then use model predictive control in order to generate good actions. So for those of you who are unfamiliar with it, model predictive control is basically a pragmatic approach to policy design. We can think of it as essentially not even attempting to build a single complex policy that works everywhere in the environment, but instead defining a very simple policy from a simple policy class and then re-optimizing this aggressively as we see new data. And we're going to take this perspective and show how this relates to online learning. Okay, so here we're going to look at how we can think of MPC as online learning. On the left, we have the online learning paradigm, and on the right, we're going to specify choices for our problem. So first, at each round of online learning, this is going to correspond to a time step in the system. That is, the learner is going to pick a new policy for every time step. And then the policy is going to be just a simple open loop control distribution. So you can think about this as just a distribution of trajectories of actions. Now note that the policy is not conditioned on state. It's literally just a distribution of action sequences. And we can think of the statistics of the distribution as the policy parameters. We're also going to assume this simplified biased simulator that's going to take the current state of the system in the control distribution as input and produce a distribution of states as output. So using a dynamics model, we can integrate the state forward in time using our policy, right? And you can see this here in the animation on the bottom right-hand corner of the screen. So the idea here is that given a state, we can evaluate the quality of a policy at that state by estimating its expected cost in simulation. So let's now look at the objective function for our task. This is on the right. So this is the expected cost under the simulated state action distribution, starting from this current state ST. And this includes terms like stay near the center of the track, drive as fast as possible, minimize acceleration. So basically, we can think of the system as picking out a loss function for our policy at the current time step. So we have this policy, and then the system's going to say, I want to evaluate this policy at this particular state, the ST that it hands us. We then play that policy in the system from that state and estimate this expected cost there. Okay, so from the online learning perspective, the objective is to now update the parameters of our policy based on this expected loss. And our goal is to minimize tracking regret. So one way to think about this is that the objective is about consistency in simulation. We want to update the parameters to perform well in simulation at the next time step. So in other words, we want to update the parameters so that the policy will have low cost in simulation wherever the system decides to evaluate me. So to accomplish this, we use an algorithm called dynamic mirror descent, which has two steps. So in the first step, it performs mirror descent to update the control distribution so that it has lower loss on our objective. That is, so that it performs better in simulation at the current state. And then mirror descent builds a convex global upper bound approximation of this objective using a gradient G, a step size lambda, and a Bregman divergence. So for those of you who aren't familiar, Bregman divergence is basically a class of divergences which includes things like squared distance or KL divergence. It then minimizes this surrogate objective. So the gradient basically tells us what direction to take to improve our parameters, and the Bregman divergence essentially keeps me close to the previous solution. So the result is an updated control distribution that performs better in the simulator at the current state ST. We then execute the first action from the updated control distribution. And the second step of dynamic mirror descent is like this dynamic part, which uses a predictive model to shift the distribution forward from time step t to time step t plus 1. You can think about this as kind of akin to a state space model and a Kalman filter. The online learning algorithm then moves to the next round, which uses the newly proposed open loop control distribution together with the next state, and then repeats. So in summary, this dynamic mirror descent approach views model predictive control from the perspective of online learning. It applies a dynamic mirror descent algorithm to rapidly adapt a very simple policy, just this open loop distribution of actions, as we traverse our state space. And intuitively, if our simulator is accurate and we can predict the next state well, then we should be able to achieve low regret on this task. So this online learning framework actually provides a very clean way of thinking about and deriving model predictive control algorithms. So special cases of this approach include LQR, cross-entropy method, and MPPI. And in each case, what we can do is just choose a policy class, pick an objective function, and then optimize with dynamic mirror descent. If you look at the details of some of these algorithms, the perspective actually suggests that many of the off-the-shelf MPC algorithms are suboptimal from an optimization viewpoint and make a number of heuristic choices that are not necessarily justified. So an example is step size, which is hidden in the MPC derivations, but is an extremely important component for getting optimization to work really well in practice. This perspective also provides a prescriptive approach to model predictive control design. So we can easily generate new algorithms that make sense for a particular application. For our racing task, we're going to use variations on model predictive path integral control. So I'm just going to show you an example of this working on the vehicle. So here you can view this as an instance of the approach. You can see the choices which are made for DMD MPC at the bottom of the screen. Essentially what we're doing is we're computing the expected cost at each state through sampling. This is GPU accelerated. And then we can use mirror descent in order to update the open loop control distribution, which we're thinking of as our policy. So MPC in general is fairly robust to perturbations. This is due to the use of a simulator at runtime to understand the local cost information and then this really fast re-estimation of the robot's state. So here you can see the robot hitting a rock, getting knocked out of alignment, and then recovering as it continues. And then finally, I just want to show that using some insights from DMD MPC, we're able to actually better tune the optimization and generate new algorithms that can reduce the number of samples needed for a task by almost 2 orders of magnitude. And this allows us to use much less compute and scale model predictive control to higher dimensional problems. So in this case, we're racing the car around a racetrack. We're only using 64 samples in our rollouts in order to understand the local cost information. This is down from 2,000 samples in the initial MPPI algorithm. And so you can get these really nice sort of improvements where you can use much less compute in order to compute very similar policies. Okay, so I just want to mention a couple recent papers on online learning, mirror descent, and MPC. If people are interested, you can take a look at these slides after the talk and learn a little bit more about what we're trying to do. All right, next I want to talk about reinforcement learning. I'm going to cover this very briefly before moving on to imitation learning. But I want to think about a slightly different problem from the one we were just considering. So here we're interested in end-to-end visual navigation. So basically mapping images from the camera and noisy wheel speed sensors directly to steering angle and throttle commands. And the AI problem here is that of finding a stationary policy that will control the car at high speeds over rough terrain without crashing. So here we're going to parameterize the policy as a deep neural network. And we have to train this network in the system somehow. So to be clear, I don't necessarily think this is the best way to solve autonomous driving problems, but the challenge reveals something about ways in which we might want to optimize policies end-to-end on difficult tasks. So at its essence, as stated, this is basically a reinforcement learning problem. The goal is to find a policy parameterized by theta that maps states or maybe observations directly to actions. And our objective seeks to find an optimal set of parameters theta which minimizes our accumulated cost. So note that the expectation here is taken with respect to the distribution of states and actions induced by the policy that we want to learn. And this is important because basically what it's showing is that we have this really kind of complicated objective function and it's non-convex, and this makes the problem very, very difficult. The cost terms here are instantaneous cost, which in our case basically says that driving slowly is bad, crashing is bad, and lots of actuation is bad. Now, interestingly, we can also view training the deep neural network via reinforcement learning as something like online learning. So every round or iteration is an episode. So in other words, we make a decision or choose a policy and run that policy in the system for some amount of time. So again, here the policy is the deep neural network itself. It's stationary, so we're going to use the same policy everywhere in our state space. And then the per round loss is the accumulated cost that the policy incurs over the episode. So similar to MPC, we're going to use a variant of mirror descent in order to minimize the loss. And I won't go into all of the details, but there's this really interesting thing where you can show that mirror descent actually defines an entire family of familiar policy gradient algorithms. And you can view all of these different algorithms from RL as just special cases of this very simple sort of online approach with a mirror descent update. In particular, different choices of Bregman divergence result in different algorithms. And this is particularly interesting because all of these popular algorithms that you see on the left here can actually be classified by how they differ in the regularization term of mirror descent. It also suggests that, at least in terms of optimization, these algorithms are fundamentally pretty similar. Now, despite the popularity in reinforcement learning, policy gradient approaches, like the ones summarized in the previous slide, do have clear limitations. So they're generally subject to noisy and biased gradients due to the challenge of estimating the objective function well, and their updates are fairly myopic. So you're just taking these really small steps towards a local fixed point in your optimization landscape. And at the end of the day, these issues mean that reinforcement learning agents require a very large number of interactions with the environment in order to succeed. Now, this can actually work for games and simulated tasks, and we've seen an explosion of deep reinforcement learning papers that use these sorts of environments for evaluation. But with real systems, training is significantly more difficult, and data is much, much harder to come by. So we can't run the robot fast in real time, and the costs that are incurred while interacting with the environment are like real costs, right? They cost me, the designer of the algorithm, something. It's not just something which is kind of theoretical that optimization uses. So we want to avoid mistakes as much as possible. So let's think about why RL is so hard to optimize. And the problem is that this per round loss is non-convex. It's hard to estimate. It requires many interactions of the system to improve to just a local fixed point. And if we could generate a better behaved loss function, training should become significantly easier. So here we have good news, right? Remember, the objective function that we use is subjective. I can choose a different objective to try to train a policy more easily. And this brings us to imitation learning. So basically, we think of imitation learning as a way to accelerate policy learning by leveraging prior information. And this prior knowledge can come in many forms, but we'll assume that it's encoded as an expert policy. And the main insight here is that expert policies will help us to define surrogate loss functions that are easier to optimize than the original RL ones. So essentially, we can compare the performance of the policy that we want to optimize to an expert policy and try to minimize the performance difference. Like, this is the whole key behind imitation learning. In practice, we can upper bound the performance difference with a statistical difference, and different divergences lead to different well-known imitation learning algorithms. If we move the evaluation of the expert policy here to the right-hand side of the inequality, like so, then we can see that we can basically upper bound our objective function. Minimizing this upper bound, we see that the first term is constant, so we can just remove it, which results in this objective function, which you can see on the slide right now. So the issue, though, is that minimizing this objective is still a difficult reinforcement learning problem. We've just changed the cost function. So it may be easier than the original problem, but it can be just as hard to optimize from a theoretical perspective. But with a small change, we can actually make this a convex function. And the key here is to change the distribution. So here, we're fixing it to be the distribution of the current policy. And the loss can now be easily convex. We can use, for example, like an L1 or L2 distance between the policy and expert actions. So going back to our online learning perspective, the per round loss with respect to the expert policy, we can see this here. We change it to this. And keeping everything else in the problem the same, we can get significantly better performance compared with reinforcement learning. So just as in MPC and RL, mirror descent, again, defines an entire family of imitation learning algorithms, where different losses result in different algorithms. So using differences in actions results in dagger, using differences in advantage results in aggravated, and different divergences result in different variations. So for example, we can define new algorithms like a TRPO version of aggravated. So now we have a way of overcoming some of the limitations of RL. Instead of noisy bias gradients, we can optimize surrogate problems which have more informative gradients, and we can actually show that we can improve towards a global optima compared with just a local optima. So just to summarize, the main insight here is that we can define surrogate loss functions that are easier to optimize. So before I return to our robotics problem, I just want to address a common question, which is, what if the expert that I'm using to train my policy is very suboptimal? Can I still use it to accelerate policy learning? And the short answer to this is, yes, you can. There's a really simple strategy, which is just use imitation learning, then do a hard switch to RL. And the nice thing about this is that this is very easy in this mirror descent framework. All I have to do is just switch the loss function at some point. And by randomizing the switching time, this performs as if running RL directly from the expert policy. Okay, so let's return to the problem of optimizing this deep neural network policy to use vision in order to control our high-speed off-road robot. So here we have our learner. We want to train a deep neural network that maps camera images and wheel speeds to steering and throttle commands. And for the expert, we're just going to use the MPC algorithm described in the first part of the talk that relies on GPS and IMU to estimate state and then aggressively updated simple control distribution. So the first algorithm relies on the MPC algorithm relies on a $12,000 sensor suite. So if we can get a neural network to drive the same way with something like a couple $100 camera, this would be pretty cool. And in fact, we can do this. So we can train the deep neural network to directly map images to motor commands. And again, it's not using any sort of state estimation or planning or replanning. It's just learning how to basically transform those images to actions by imitating the MPC expert. And what you can see here is that it can robustly pilot around the track at roughly the same speed as the MPC expert. Okay, so here are just some recent papers from our group on imitation learning if you want to learn more about some of this stuff. But we're looking at a lot of kind of interesting relationships between imitation learning and reinforcement learning and how to try to make things more efficient. Okay, so let me just briefly summarize some of the key points from the talk. So first, online learning is a perspective that can serve as a unifying framework. And the main takeaways are that it provides simple derivations and insights from optimization to suggest new and better algorithms for problems like model predictive control and imitation learning. Model predictive control is a really effective approach to handling challenges like complex dynamic environments, and it's able to, you can think about it as doing something like optimizing a very simple model aggressively. And again, it's very effective in practice. Reinforcement learning allows us to learn very complicated policies for extremely difficult problems. It is state-of-the-art in games, perception, and natural language processing. And it's really important that we pay attention to it. So data is revolutionizing how we attack fundamental problems, but the key is understanding how to generate data in a cost-effective way, how to leverage that data, and how to exploit structure in our problem. And this is generally not easy, and I think a very interesting area of research. And then finally, imitation learning is a very general way to accelerate policy learning. So it provides a way to leverage models or simulators or other types of expert knowledge, so humans. It also can be viewed as a way of combining strategies. So if I can write down if I can write down a policy which solves a problem in a particular way, I can potentially learn from that and improve on it using imitation learning and reinforcement learning. It allows us to leverage surrogate objective functions, which are easier to optimize. And this is something that we should always be thinking about for our robotics tasks. All right, finally, I just want to thank this awesome interdisciplinary team of robotics PhD students in computing and aerospace engineering and electrical engineering. They come from University of Washington, Georgia Tech, and CMU, who have been working on the tasks that I presented today. And I particularly want to thank Wen Sun, who is a student at CMU, who's now a professor at Cornell, who was doing a lot of the collaboration on imitation learning. All right, thanks a lot.
Thank you, Byron. Very insightful talk. I really liked your results unifying a number of previous results in the field of learning-based MPC, reinforcement learning, imitation learning, and so on. We have time for a few questions. For the audience, you can submit your questions either through the Q&A functionality or directly in the chat, and I will read them directly to Byron. So we have a question from David Conner. The question is, can you discuss how transferring the trained DNN approach to a new track compares to transferring the MPC approach?
Yeah, so the MPC approach transfers very well compared with trying to transfer a neural network or like a deep neural network, which is mapping images to actions. And the reason is because the MPC algorithm basically uses a very general notion of state, right? So information about the robots like position, velocity, accelerations. And this is something that is just more general, easier to base an algorithm off of. And like basically all we need to do is make sure that we have a good dynamics model for both tracks, and we can just let it go. Whereas if you're training a neural network, like a deep neural network to map images to wheel speeds, then you have to make sure that that network can handle the entire variety of images that you may see. So if we're training on one track and that track has different visual properties compared with a second track, then the algorithm is just not going to the learned model is just not going to transfer. So you can't escape this notion of having to sort of train and test on similar types of distributions. You'll have to have seen similar images before, and they'll have to mean similar things in terms of the actions that you take in order for transfer to happen well.
Okay, great. We have another question from Andy Park. First of all, he's complimenting for your talk. Are you using any off-the-shelf solvers, and what is the current computational cost of the algorithms that you presented?
You know, it depends. I mean, you should use basically whatever optimization algorithms are sort of most efficient, subject to, you know, setting things up the right way. For mirror descent, for some of the approaches that we are using, you can actually come up with very fast ways of updating the parameters of your policy without necessarily, you know, having to use a like complicated off-the-shelf solver. So for a lot of the stuff, we're basically deriving an appropriate update to the policy parameters and just have an efficient way of doing that by hand. I think if you were going to use something like, you know, trying to optimize something with a QP or whatever, then you should use something which is off the shelf. But for some of the algorithms which I described today, we're basically doing the optimization, or we're you know, writing down a efficient optimization algorithm and just kind of doing it ourselves.
Thanks. So we have a question that is very important. He's addressing the sim to real gap. Specifically, Fahad Islam is asking, how were you going about bridging the sim to real gap? And you know, you had this arrow going from the system to the simulator, but what was happening there under the hood?
Okay, so this depends on the problem, right? So I think addressing the sim to real gap is super important problem. And I didn't discuss this, oops. Okay, I didn't discuss this like all that much in this particular talk, but there's a few things to think about. So there's these different scenarios where you can use the simulator effectively. So one is I have a really accurate simulator and I can do something like train a policy in simulation, then take that policy, move it into, or move it onto a real system, and then, you know, try to do some additional optimization in order to get that policy to work well. But another approach is to be using the policy use the simulator while I'm executing the policy. And in this case, I will almost certainly have a fairly simplistic simulator or a fairly simple model, which allows me to predict something, but it's not going to predict something which is particularly accurate, maybe just something which is useful. So these are sort of two different scenarios, right? One where I'm trying to use the simulator to make very fast, inaccurate, but maybe useful predictions versus thinking about the simulator as like a full stand-in for the real world. And the way that you may address sim to real transfer might be different in each of these cases. So on the one hand, if the simulator is very accurate, you know, maybe what I want to do is basically system ID or figure out some way of trying to adjust those parameters so that I get more and more accurate predictions. And then maybe I also want to do something like a little bit of imitation learning or reinforcement learning after I transfer the policy from simulation into real world in order to refine it. But for a simulator which is not particularly accurate, then I think we have to do something which is maybe much more interesting and maybe aggressive. So the idea would be to try to think about how the world can correct for the biased predictions that the simulator is making. And there's maybe a number of ways of doing this, but you know, one way is saying, look, I'm going to get a gradient from the simulator to update my parameters. I know that that's biased. Can I use this as a prediction about what I expect to experience next? Like, what is my next loss going to be? And then use the real world data in order to correct for that biased gradient, right? So you can imagine like all sorts of scenarios where you're trying to learn like a residual model, you're trying to correct correct biased updates to your policy using real-world data. I think this is a fairly interesting and open area of research. But I think the key is, in my mind, like, all simulators are wrong. The idea is that, sort of paraphrase Box, right? Like, all simulators and models are wrong, but some of them are useful. So how do you use this incorrect, biased, wrong data in a useful way in conjunction with real world data in order to boost performance? We've worked on a couple problems related to it, or a couple solutions related to this, but I think this is still a fairly open area of research.
Thanks. And we are almost out of time, but let's see if we can squeeze one or two additional questions. So one question is from Shreyas Kuzik, and he's asking, how do you initialize the policy distributions for the MPC approach where you don't necessarily have an expert, and how sensitive the MPC approach is to that initialization?
So the MPC approach has a number of different parameters. We're thinking about the policy as basically just being a distribution of action sequences. And so you can initialize this as a very sort of wide Gaussian. So at a particular state, I have a Gaussian with a large covariance. And then what I want to do is, as I receive information from my simulator and as I run my algorithm, I want to update the mean and covariance, for example, of that Gaussian in order to refine that policy. Now, part of this, the algorithm is also like the dynamics model, right, and the simulator that you use. So this will affect the accuracy of the solution that you have, and how kind of quickly you can update your policy. I think there's a trade-off here. You can use a very accurate simulator or model, but now you're going to be able to do fewer rollouts, and it's going to take more compute. You should obviously try to set the parameters of that as accurately as possible. I'm not sure that like totally answered the question, but yeah, that's.
I think that's certainly useful insights. Yeah, there are some additional questions, and personally, I would have quite a few questions, but unfortunately, we have to wrap this up. So I would like to thank you again, Byron, for a very insightful talk, and hope to see you soon, hopefully in person.
All right, thanks a lot, Marco. Thanks, everyone.
Bye-bye.
Bye.